Okay, great. Good morning, afternoon, or evening, everyone, depending on where you are. Welcome to the online seminar organized by the Department of English and Communication, Hong Kong PolyU. Today, we're really happy to have, sorry, let me try to do this right. Professor Eleanor Chodroff, right? It's a postdoc Viola.
Yeah.
Okay.
Yeah. No, it's perfect. Yeah.
Okay, thank you. So Professor Chodroff is an assistant professor in the Department of Computational Linguistics at the University of Zurich at the moment. So where she leads the Phonetics and Cognitive Science Lab. And her research focuses on the phonetics and phonology interface, cross-talker and cross-linguistic phonetic variations, speech prosody, and speech perception. And when she's bored, she also looks at more for phonology. So she regularly uses computational techniques and large-scale data processing to understand cognitive and machine representations of speech and voice. So before joining Zurich, she was a lecturer at the University of York and a postdoc in Northwestern University. And she received her PhD in cognitive science from Johns Hopkins University and BA in German and linguistics from New York University. So today, the talk is titled Intrinsic Vowel Effects Across Words Languages. So without further ado, so please, Elena.
Yeah, thank you so much, Bruce, for the introduction. So today's talk contains a lot of joint work with a postdoc who's working with me, Miao Zhang, who's also at the University of Zurich. So the first thing I want to talk about is, as in day-to-day life, we are all very familiar with the fact that people's voices vary a lot. Human speech is highly variable. And one phonetic dimension that is really salient to listeners and also is of interest to phoneticians is that we perceive as pitch. And pitch we can acoustically measure as F0. And there are some speakers who have really low-pitched voices, like Morgan Freeman.
I'm Morgan Freeman. And when I communicate, I usually do so through deep, weighty, and profound voiceover.
Okay, and of course, having a low-pitched voice isn't just associated with male speakers. Female speakers can also have very low-pitched voices.
Today I had the pleasure of watching you in the afternoon, and it was just incredible. It's the same feeling.
And then on the other hand, on the other end of the spectrum, we can have speakers with very high-pitched or high F0 voices, like Jenny Slate.
And the answer is, certainly not, is what I was.
Or Chris Colfer.
It was like a cylinder shape.
And as phoneticians, we can find lots of phonetic dimensions that we can quantify how much people's voices differ from one another. What I'm interested in is, are there universal constraints on how much our voices are allowed to differ from one another? So speakers can differ on almost all possible phonetic dimensions and for all possible speech sounds that we can produce in our language. And so I want to take this one step further and say, okay, but where are the limits? And where are the limits beyond just what biology puts on us? So are there constraints that govern the projection? So how exactly phonological segments, so sounds like E or ah in a very abstract sense, are there constraints that govern the projection of phonological segments into a phonetic space that we can then physically measure? And if so, what are those constraints? So I'm actually going to give you an overview of how I think about the phonetics-phonology interface as it operates in the mind of a speaker. This is just one assumption. There are lots of possible ways that this could work. But for today's talk, I'm going to be assuming this type of interface. So in our mind, when we're trying to produce language, we might have let's say we're speaking English, and I need to differentiate the word Pete from Pat, okay? I might have a representation of an E sound that is composed of distinctive feature values that are very abstract, that in order to say this word, I'm going to need this linguistic unit. And this phonological representation is a very traditional one. And it might tell you something about the phonetic specification, but it doesn't tell you exactly how high the tongue should be, how far forward. The vocalic feature might tell you that, okay, maybe you should be vibrating your vocal folds, but I'm not going to tell you to what degree. And maybe it should be minus, the lips should not be rounded, but I'm not going to tell you to what extent. Those detailed specifications that are still abstract, I think of those as being the phonetic targets. So this mapping from the phonological surface segment to the intended perceptual motor goals of the production is a process I call phonetic realization. And in the phonetic targets, we'll get an exact specification of, okay, where exactly in the mouth should the tongue be? How high is it? How back is it? How much jaw force do I need to send, and at what duration? What should be going on at the vocal folds? Should they be vibrating? For how long? At what rate? And what should the lip rounding be doing? Okay. And then once you have those, it's sent off to articulation, which is something physical that we can measure. And correspondingly, it creates an acoustic signal that I'll be actually working with today. Now, when we think about constraints, they're on this mapping from the phonological surface segment to the phonetic targets. Again, there's lots of variation in the world's languages and across speakers of a given language. Are there constraints on how this mapping happens? So for sounds like E and Ah, which we'll be focusing on today, their main difference is in tongue height, right? They're both vowels. And the vocalic feature, the fact that they're both plus vocalic or whatever feature you want to call it, might correspond to, okay, whatever's going on at the glottis, that's going to be the phonetic target. So the laryngeal setting. What should the vocal fold vibration be? How long should it be for? And then they mainly differ in the height features, which of course seems reasonably controlled by where exactly the tongue is. We can think that the one way of thinking about this is that a distinctive feature value gets mapped to a single phonetic target, okay? So there are independent mappings between the feature values, like plus vocalic going to glottis features, and tongue height features going to tongue height targets. And we can also think about two constraints, functional constraints that have been proposed in the literature that might restrict variation. These two constraints are distinctiveness. So of course, when you produce speech, you need to be able to convey the difference between an E sound and an Ah sound, right? It's fundamental to contrast in most of the world's languages. And so of course, we need to make sure that whatever the mapping is from this feature over to the phonetic target is, those phonetic targets need to be very different from one another so that we can perceive the difference, okay? And so there's something saying make sure that these phonetic targets are very different, okay? But with the plus vocalic feature, we might have a constraint of uniformity, which is sort of like an economy principle. Why create new? So one idea is that we could create a new phonetic target for each of E and for Ah with respect to what's going on in the glottis and the laryngeal setting. Or we could just reuse whatever phonetic target for Ah that we created for E, right? Simple reuse, economy, make sure that the mapping from the plus vocalic feature to all segments to all phonetic targets that are mapped to that feature, make sure they're the same. A slightly more complicated picture that's going to be relevant for today is that actually the mappings are not so one-to-one, and the phonological features can have control over multiple phonetic targets. Okay, this means, so the height features can also kind of have a say in what's going on in the larynx. So then we might also have not just pressures of uniformity saying, if there's a shared feature value, make sure the mapping from the shared feature value to the phonetic target is the same across all sounds. So all vowels should have basically the same fundamental frequency or whatever phonetic target is underlying that, the same duration or whatever phonetic target underlies what we measure as duration. But distinctiveness now, which is again another important functional principle in language, is saying, well, why don't we just make everything different so it's really easy to perceive the contrast between all of the speech sounds in a language? And if we make everything different, then speakers can vary a lot. And hey, that's really good for both communicative purposes and for being able to tell people apart and so forth. Okay, so I want to be able to test these principles in across the world's languages. But in order to do so, we first need to get some data. And cross-linguistic phonetic resources have been extremely limited until the past few years. Okay, so we have two functional principles, uniformity and dispersion. It sounds like maybe they should be present universally, but again, it would be good if we could actually test that out across a diverse range of languages. On the screen here, you can see that from 2008 to 2025, the landscape of cross-linguistic phonetic resources has changed dramatically. So the earliest truly cross-linguistic speech corpus that I could identify was back in 2009 with the UCLA Phonetics Lab archive. And that is to date one of the most diverse speech corpora, but it is limited to about one speaker per language. Then in 2013, we've got the global phone corpus, which has 20 languages, but it is very expensive. And from 2019 on, we get this explosion in what have been called massively multilingual speech corpora. And the corpus that I'm going to be focusing on today is the Mozilla Common Voice dataset, which has over 100 languages in it. And basically, it started in 2020, and they release new data and new languages every 3 months. Okay, and it's completely crowdsourced. Okay. So the Mozilla Common Voice corpus has over 100 languages in it, and anywhere from less to 1 hour of data to over 3,000 hours of speech per language. And it has anywhere from a handful of speakers to thousands of speakers per language. And you can go to the website right now and contribute to this process because it's entirely crowdsourced online. And that's from the sentences. You can either write sentences for people to read or produce sentences, so record sentences that actually go into the corpus. And you can also listen to sentences that people have recorded and provide this validation procedure and basically indicate whether the person speaking actually produced the correct transcript. Okay. And yes, there's a new release every 3 months or so. Okay, so you can just go and download this corpus. It's very straightforward to download, but the download includes the multilingual audio and it has some transcripts, but that does not necessarily mean that it's ready for phonetic analysis. So once we download it, we then have created a pipeline to be able to work with the corpus and work with it at scale and basically be able to then extract, say, all of the E sounds in the world's languages or all of the ah sounds in the world's languages and take measurements from them. In order to do that, we first apply what's called grapheme to phoneme conversion. Again, we have an orthographic transcript. We then need to convert that into a phonetic transcription. And we've been using a canonical phonetic transcription with, and there are several toolkits that will do this mapping between a language's orthography to the most canonical transcription. Once we have that, we can then train an acoustic model to do phonetic forced alignment and automatically time align the phonetic transcription to the corresponding audio signal. And that gives us this forced aligned transcript. We only do this for languages that have at least 2 hours of data per language, and we only work with the portion of Common Voice that's been validated, which is where at least 2 listeners have indicated that the person doing the recording indeed read the transcript correctly and that it is an audible recording. Okay, and to give you a sample of what this looks like at the end, I've got some text grids here and recordings from various languages. So this is Amharic. It's spoken primarily in Ethiopia, and you can see the original word level transcript as well as the canonical phonetic transcript. It sounds like this. Okay, I'll play that again. And this was all done automatically through some toolkits. Here we've got Czech, an Indo-European language from the Czech Republic. You can see again, we've got the IPA symbols at the bottom so that if we're interested in the E sounds, we can locate their occurrence. And Japanese. Okay. And Guarani, which is the one language we have from the Americas, spoken primarily in Paraguay. Let's see. Okay. So all in all, we've processed about 75 languages, and we've named this derivative phonetic corpus the Vox communis corpus. The 75 languages are from 18 language families, which you can see listed over here, how many we have, and you can also see where the languages are primarily spoken in the world on the map here. The text grids are freely available on our Hugging Face repository, and you can download the audio directly from Common Voice if you are interested in working with this data set or one of the languages. We've also done similar processing for the wilderness corpus, which is Bible speech from over 600 languages. It's extremely diverse, but it also has the limitation where many of the languages are represented by only one speaker. But we've called this the Vox Clementis corpus, and there are about 48 high-quality languages where we have reasonable trust in the G2P. And also for the UCLA Phonetics Lab archive, we've manually cleaned up, or there's been some automatic processing, but we did an additional manual cleanup of the IPA transcriptions and forced alignments, which we've called the Vox Angeles corpus. And those are also both available for download. Okay, so now we've got some theoretical questions and we've got some data that we can work with to start answering some of those questions, like is uniformity a constraint on the projection from phonological segments to phonetic targets across the world's languages? Is dispersion present? To what degree are they present? And we have data. So we're going to look at two what are called intrinsic vowel effects, starting first with a previously proposed phonetic universal that's actually had a fair amount of empirical support so far, which is intrinsic vowel F0. Intrinsic vowel F0 is the observation that high vowels such as E and U tend to have a higher F0 compared to low vowels such as A. And the first truly cross-linguistic study to look at this was a meta-analysis from Whalen and Levitt, 1995, where they collected previously reported data points from 31 languages and 11 language families. And they found that in all of those languages, there was 100% conformity. It was always the case that the high vowels did have a slightly higher F0 compared to low vowels. One limitation, there was just a few speakers per language. Similarly, Ting et al. 2025 also conducted a large-scale corpus study, 20 languages, just 8 families. They also found that all of the languages showed this empirical effect. And then in one of our studies using the Vox Angeles corpus, we also looked at 53 languages and 17 families, but only found 74% conformity. The major issue with this study was that we only had one speaker per language and only a handful of data points. So we'd like to maybe expand on this empirical foundation with a larger empirical foundation and also really investigate some of these theoretical questions about what governs this regularity. So one other thing I want to point out with F0, as you might, one consideration when you hear about this effect is, okay, it's a small difference in speech, who cares? We started off this talk with the variability that occurs in F0, just along one dimension, that speakers can differ a lot in F0. And F0, again, is one of the most perceptually noticeable and variable dimensions of speech. It can convey so much about our speaker emotion, speaker identity. So there are lots of extra linguistic functions of F0, and there are lots of linguistic functions of F0. English and many languages use F0 regularly to convey differences between statements and questions. Many languages use F0 to convey word meaning contrast, so lexical tone. F0 varies a lot. And yet, what the literature is telling us is actually it varies a lot, but there's this regularity and consistent difference that occurs across almost every language. Why does that happen? Does that tell us something about the constraints on how much we're allowed to vary F0? So there have been two primary explanations for the source of the effect. The first is what's called the biomechanical explanation, which is that this is an automatic effect. And the one useful explanation for this is the tongue pull hypothesis, which is that the result arises when holding all else equal in articulation, the raised tongue of the high vowel could pull on the vocal folds, resulting in a higher F0 for high vowels than low vowels. Okay. On the other hand, it's traditionally framed as an unintentional consequence of articulation. On the other hand, there's the perceptual enhancement explanation, which is that speakers intentionally differentiate the F0 between vowels like E and A for perceptual facilitation of the vowel height contrast. And then there's also an idea that speakers could intentionally specify phonetic targets underlying high and low vowels independently, which could result in either this perceptual enhancement explanation or even minimization of the effect. So this automaticity or biomechanical explanation versus the speaker control or enhancement explanation, I'm going to reframe it just minorly. So historically or traditionally, automaticity is commonly contrasted with speaker control over the effect. What I'm going to reframe this as is actually automaticity is a type of uniformity. The key difference, though, is that uniformity requires control over the specification of the targets. So an alternative characterization of a type of automatic account is that some phonetic target that underlies what we measure as F0 is controlled to be the same across multiple segments, and then physics happens on top of that. So there's a minor F0 difference that results when we actually look at the acoustic signal. And what's really important is actually if you look at the literature that's talked about the automatic effect, they kind of this is one of their assumptions. They almost always have a phrase saying holding all else equal. This is uniformity. If we assume that the speaker sort of intended for the laryngeal setting to be the same across E and A and U and all of the vowels, then when that is sent off to articulation, the raised tongue that's critical for the vowel height contrast, so the E high tongue versus A low tongue, that raised tongue for the E could pull on the vocal folds, and then you measure a higher F0 for high vowels than low vowels. But this is all based on the assumption that you were trying to be economical in the phonetic targets. Reuse the laryngeal setting for E, for A, for U, and so forth. Okay, so what this looks like on the phonetics phonology interface is that, okay, yes, the tongue height should differ between E and A. That's critical. That's not going to be debated. And the idea here is that the fact that E and A are both vowels, well, maybe just maybe whatever phonetic target you set that controls the F0, so H1 and H2 for A, those should be the same. And that's uniformity, okay? What the perceptual enhancement account is arguing for is actually, well, given that maybe we also want to make the difference in F0 between E and A a little bit different to help out in the overall contrast between E and A. So this additional line is almost the one that's sort of like, is it present? Is it, and how strong is it? Okay. So we're going to be testing this circle that yokes together the phonetic targets for the glottis of E and A, and whether there's also a pressure to actually make those different across languages. So in the present study, we're going to use the Vox Communis corpus to investigate vowel intrinsic F0 and look at the extent of cross-language and cross-speaker variation. And specifically, uniformity predicts a consistent difference in F0 between E and A in the automatic direction. So E should have a higher F0 than A. And critically, there should be no difference in F0 between E and U, right? Because there's no biomechanical explanation for an F0 difference. Enhancement, on the other hand, predicts an exaggerated difference in F0, at least between E and A, and potentially also just much more variability in the magnitude, suggesting that speakers or languages could really make the difference extra big, or they could make the difference small. Uniformity is saying, okay, well, it should be pretty stable if it's just an automatic consequence of a uniform articulation. Also, in support of enhancement, we're going to look at whether there's a relationship between the language's vowel inventory size and the magnitude of the difference between E and A. The idea being that if you are in a language that has many vowels, so the F1, F2 space is already very crowded, then it might be in your interest to use additional phonetic cues to enhance the difference between E and A. And finally, we also want to look at how the presence of lexical tone might influence the magnitude of the VF0 effect, with the idea here being that in lexical tone languages, F0 is already under precise control for lexical contrast. And if F0 is already being used for additional phonological contrasts, then maybe it's less available to use as additional enhancement for the vowel height contrast. So very briefly, our methods were to take the average F0 measurement from the middle 10% of E, U, and A, and we retain tokens within about 1 octave of a speaker's mean, speakers with at least 10 tokens per vowel region, and languages with at least 5 speakers. And today we're just going to be looking at the E-A and E-U comparisons, where we have 75 and 72 languages respectively. So on this slide, we have the results for E and A. And the first figure I want to explain is this figure A here with all of the languages ranked. And this is the size of the VF0 effect in each language ranked by language. So the orange line is if there is no F0 difference between E and A. So there's no difference. And the point represents the difference. If the point falls to the right of the orange line, then the language does indeed conform with the expected direction, where the E F0 is higher than the A F0. Okay? If the point is blue, then it is significantly different from 0. If the point is orange, it's not significantly different from 0. And we also have each of the languages labeled by what tone system type they have. So purple is a simple tone system, and blue is a complex tone system. Okay, what you can see is that 97% of the languages numerically conform with the expected effect, and 88% of them are significantly significantly so. They're significantly different from 0. There's a median of about a 0.5 semitone difference between E and A. To put that into perspective, 1 semitone is a half note on a musical scale, so it's about half a half note, okay, or a quarter of a whole note. And the non-conforming languages that we observed were Bashkir and Japanese down here at the bottom. On the right-hand side, we have the proportion of speakers who conform to the effect, where anything in blue represents the proportion of speakers that are going in the expected direction. Orange represents the proportion of speakers going in the unexpected direction. And you can see that the chart here is almost entirely, the majority is blue, and the minority is orange, and very few speakers are differing significantly from 0 in the unexpected direction, represented by the dark orange. Okay. Turning to EU, we get a very different picture. For EU, we can see that languages are almost centered around the line representing 0 difference between the F0, and the median is actually 0. And it is about a 50-50 chance of whether a language is going to have a higher F0 for E or for U, okay? Same with the proportion of speakers. It's a coin toss of whether a speaker is going to have a higher F0 for E than for U, okay? Moving on to vowel inventory size, we can see the correlation. So we've got the number of vowels on the x-axis and the VF0 estimate on the y-axis. And we can see that for the vowel height contrast, as the number of vowel increases, the VF0 magnitude also increases slightly, but not significantly. That said, there's a very big difference between this minor positive correlation on the left-hand side with the very flat line that we observe on the right-hand side between E and U, where there's no relationship at all there. Now for tone, overall, tone languages tend to have numerically but not significantly lower VF0 estimates in the high-low comparisons. So the black here is the non-tonal languages, and in general, they tend to have slightly larger VF0 effects than the simple tone in magenta and the complex tone languages in cerulean. These are not significantly different, but we might need more data and control over the tone language estimates to really be able to tease apart what's going on there. So in summary, we have high cross-language and cross-speaker conformity with the VF0 effect, but we also observe considerable cross-language and cross-speaker differences in magnitude and no observable bias between front and back vowels. There's also little enhancement with vowel inventory size, but actually it maybe, that said, the findings are extremely consistent with previous findings that everyone seems to be finding this really small positive correlation. So maybe there is a small amount of enhancement present there. And there's also a numerical but not significant relationship with tone, which is also extremely consistent with previous findings, especially for the observation that Mandarin seems to consistently stand out as having a small VF0 effect. And this maybe these results are driven mostly by Mandarin, okay? That's something we should look into as a community. Okay, so moving briefly on to the second effect, I'm going to go a little bit more quickly through this, but these results largely parallel the F0 results. A sister effect to VF0 is intrinsic vowel duration, which is the observation that high vowels such as E and U tend to have a shorter duration compared to low vowels such as A. Okay, so this is, again, the setup here is going to be very similar. One of the main differences, though, between intrinsic vowel duration and intrinsic vowel F0 is that the amount of empirical evidence for intrinsic vowel duration has been much more limited. So on this slide, I've tried to document every comment or empirical observation that has been made with respect to this effect. And you can already hopefully see that the number of speakers that they were measuring durations from is very small. And also the number of languages they've been able to document this effect in is also fairly small. We've also got a huge bias where most of these languages are Indo-European, so on the left, not just Indo-European, simply European. And the ones on the right represent the non-Indo-European languages. And we can see that it's a very few data points to support this observation. Now, why are phoneticians still okay saying that, yeah, we think intrinsic vowel duration should exist? Well, it's very similar to the intrinsic vowel F0, where there's a biomechanical explanation for its existence. And this has to do with, one explanation has to do with the fact that the duration, if you keep the duration of jaw movement the same across high vowels and low vowels, well, low vowels have a lower jaw displacement, so A compared to E. And when you time that up with co-articulation, you then would automatically predict that low vowels, due to the jaw lowering, should have a longer duration than high vowels. Okay, so this is the explanation. And again, it lines up with, is uniformity and automaticity what's controlling this variation? Or are languages and speakers allowed to enhance the difference to some degree? Okay, just like with VF0. So we're going to look at this again. We have the exact same predictions as before, but we'll just be looking at vowel inventory size and vowel duration in the end. So when we measure the durations, and we've controlled for speaking right here, we find that 89% of languages in the 82, there are about 60 some languages in this, but 82 phonological contrasts. So some languages, of course, have long vowels and short vowels. 89% of these contrasts conform. Again, an overwhelming bias for a language and also a speaker to have a shorter duration on E than for A. Okay. That said, there are a few more languages that go in the opposite direction, which we've started to look into. We have explanations for maybe 2 of them, but certainly not all of them. I think there's a lot of follow-up work that should be done here. But again, we're getting this small, consistent difference across languages. For E and U, very similar to the F0 results, it is a coin toss whether languages are going to have a shorter E than U or a longer E than U, as if uniformity is saying, okay, if there's no biomechanical reason for there to be a duration difference, maybe just reuse the duration for E that you did for U. If it's a vowel, just keep the duration the same. So in summary, we have high cross-language and cross-speaker conformity with the effect, which is predicted by uniformity, showing that yes, an automatic explanation, assuming that speakers intended for the phonetic targets to be the same, that explanation is probably very strong, and there does seem to be a fair amount of evidence that that's a constraint on phonetic realization. That said, there is some data that we can't explain with uniformity alone. This is that there are differences in the magnitude. Some languages have extremely huge differences in the magnitude of the effect, whereas others have very small. Same with the speaker conformity. This suggests that speakers and languages might actually have a little bit of control to further enhance the automatic effects, so make the phonetic targets for the laryngeal setting a little bit different, or to make them even more the same in the acoustic output. Okay. There's also no observable bias between front and back vowels. That's the uniformity. And while I didn't present the data here, we found no enhancement with vowel inventory size for vowel duration. This is a difference from the vowel F0 results. When you look at the relationship between the number of vowels in the language and the intrinsic vowel duration magnitude, it's a flat line for all 3 pictures. So is this all uniformity or is it enhancement? Why not both? Okay, so I say this tongue in cheek, but there is an amount of seriousness there. The general takeaway that our interpretation of these findings is that there's definitely a strong influence of uniformity on F0 and duration. The fact that we do get a bias consistently in the direction of the regularity, as well as the fact that it's still a small difference. This is showing, again, it's physically possible for me to produce E with a consistently low F0 and A with a consistently high F0, and yet almost no language does that. Same with duration. It's physically possible for me to produce the opposite effect, yet again, we're not finding much evidence for that. We're contributing that to uniformity. That said, there's slightly more evidence. There is some evidence for minor role of enhancement. So we can't fully explain the fact why it is that there's so much variability in the effect and the correlation between vowel inventory size and the VF0 effect. There is some evidence suggesting that speakers have some control that they can make those phonetic targets a little bit different, which would violate uniformity. Okay, but it's minor. So why should we care about these effects in general? Again, these are very small effects, but given how much variation there is in phonetics, how much we can vary in F0 from speaker to speaker, from day to day, from sentence to sentence. There's so much variation, and yet when we find something that's so consistent, if there's something consistent in the acoustic output, that suggests that there's something consistent that's organizing the way that we produce speech. Okay, so these findings reveal limits to phonetic variation and potentially shared influences on our very language-specific phonetic representations. Okay, so in the future, we would love to get more languages overall, but especially from the Americas. In our sample, we unfortunately only had one language from all of the Western Hemisphere. We would also love to know more about what's going on with non-conforming languages. And because a lot of these arguments relate to perceptual effects, like maybe people enhance the difference for easier perception of the contrast, we would also like to follow up some of these speech production studies with speech perception studies. And also look at in what other ways these constraints like uniformity and dispersion and how they operate on the phonetics phonology interface might also influence the degree to which sociophonetic or speaker variation might exist. Are there constraints on speaker variation due to some of these same constraints? So thank you all so much for listening to the talk and for inviting me here today. And thanks to many contributors and collaborators in the funding for this study.